students, I am Chaitanya, Assistant Professor in Mathematics, working in Institute of Aeronautical Engineering located at Dundigal, Hyderabad. As a part of our course curriculum, Probabilistic Reasoning and Modeling, we are discussing the concept of singular value decomposition. In the last class, we have discussed what is a singular value decomposition of a given matrix and how it is related to eigenvalues and eigenvectors, and what is the relation of singular value decomposition to principal component analysis, and how it is vital in reducing the dimensions of a given sparse data matrix and its applications of its applications in image processing and digital signal processing, etc. And today we are going to see a worked out example on singular value decomposition over a 3 by 3 matrix. So let us look into the things in detail. So here let us recap what is a singular value decomposition. When we are given with a matrix A m by n, we can decompose it into product of 3 matrix U, D, V transpose, where U is an orthonormal matrix and D is a diagonal matrix and V is an orthonormal matrix transpose. So singular value decomposition is the thing, but writing A as a product of 3 matrices where U is an orthonormal matrix, D is a diagonal matrix and V is another orthonormal matrix, and product of these 3 things will be approximately equal to the matrix A. That is called singular value decomposition. And we know that it is a very handy mathematical technique because it just involves matrix multiplication, norm of vectors, product of vectors, and transpose, and multiplication of matrices. So it is not at all involves any intrinsic calculations of mathematics, and it is why it is a very handy mathematical technique, and it is easily programmable to computers, and hence it is very important in mathematical learning, machine learning. And as we just discussed, U is orthonormal, W is diagonal, and V is orthonormal. Let us just recap what is the meaning of orthonormal matrix and diagonal matrix. See, a matrix U is said to be orthonormal matrix. Well, first, it should satisfy 2 conditions: orthogonality and normality, unit normality, imprecise. What is orthogonality? Suppose U is a matrix of 3 columns Q1, Q2, Q3, where Q1 is called as a vector, Q2 is called another second vector, Q3 is called third vector. Orthogonality means Q1 dot Q2 is 0, Q2 dot Q1 is 0, and Q3 dot Q1 is 0. And unit normality means norm Q1 is 1, norm Q2 is 1, norm Q3 is 1. So if the matrix satisfies 2 conditions, namely every pair of vectors orthogonal to each other, that is dot product of Q1 Q2 is 0, dot product of Q2 Q1 0, dot product of Q3 Q1 0, that is orthogonality, and the norm of each vector is 1, that is unit normality. If the matrix satisfies these 2 conditions, then it is called orthonormal matrix. Orthonormal matrix. So here in singular value decomposition, our left corner matrix and right corner matrix, both U and V, are orthonormal. And let us look into the meaning of diagonal matrix. The middle matrix W is a diagonal matrix like W1 0 0 0 W2 0 0 0 W3, like that means except the diagonal elements remaining all zeros. Such kind of matrices are called diagonal matrix. Here the elements in this W, that is the diagonal elements in this W, are called singular values, and they are always non-zero, okay, or positive or 0, but cannot be negative. So W1, W2, so on Wn are either positive or 0, but cannot be negative. And these are called singular matrix, and hence this decomposition is called singular value decomposition of the matrix A. Okay. And these matrices U and V are obtained from the eigenvalues and eigenvectors of the matrix A into A transpose or A transpose into A. The eigenvalues and eigenvectors of A into A transpose will gives us U, and the eigenvectors of A transpose into A gives us V. Okay, and W is obtained from the eigenvalues of A into A transpose. This is what we can say in brief about singular value decomposition. Let us look into the mathematical process. This is just a representation of A as singular value decomposition U into V into U into W into V transpose. Okay, and among the values W1, W2, so on Wn up to W are only non-zeros, remaining all zeros. Okay, because the rank of matrix A is R. So if the rank of the matrix A is R, then out of n values, only R values will be non-zeros, remaining values will be zeros. And SVD, singular value decomposition, is one of the several techniques that can be used to reduce the dimensionality which we have discussed in the last class. To reduce the dimensions, that is the storage space of a data set, we can use singular value decomposition. And while SVD can be used dimensionality reduction, it is often used in not only dimensionality reduction, it also used in digital signal processing for noise reduction, in image compression, and other areas also. Now, let us take an example here. How to calculate the singular values of the matrix. Question is, find the singular values of the matrix A. Singular values of the matrix A. How to calculate those singular values? First, for calculating the singular values of A, we need to calculate A into A transpose. That is, we have to multiply 1 to 1, 2, 3, 2 and 1 to 1 with the matrix, the transpose 1 to 1, 2, 3, 2 and 1 to 1. Here, fortunately, we have A is a symmetric matrix. We can see that these elements 2, 1, these are 2, 1, this is 2, this is 2. That means A transpose is equal to A. We can easily verify this is a symmetric matrix. And hence, A into A transpose means we are observing that both are same. When we multiply these two matrices, we get this matrix, first row, first column, that is 1 square, 2 square, 1 square, that is 6. And first row, second column, 1 into 2, 2 3s are 6, 1 2s are 2, that is 10. Again, first row, third column, 1 1s are 1, 2 2s are 4, 1 1s are 1, that is 6. Similarly, second row, first column, 2 1s are 2, 3 2s are 6, 2 1s are 2. And second row, second column, 2 2s are 4, 3 3s are 9, 2 2s are 4, that is 70. And second row, third column, 2 1s are 2, 3 2s are 6, 2 1s are 2, that is 10. And similarly, third row, first column will get 6, and third row, second column will get 10, and finally 1 to 1 into 1 to 1, that is, will get 6. Okay, this is our A into A transpose. Now, for calculating the singular values, our mission is to calculate singular values of A. That is our question. How to calculate singular values of A? So, for that, we need, when we get A into A transpose, we'll consider the matrix A into A transpose minus A into A transpose minus lambda I, which is nothing but minus lambda minus lambda minus lambda. This is called characteristic matrix. And if you write det, we can calculate det of this matrix. That will be a polynomial. Because it is a 3 by 3 degree matrix, we'll get a polynomial like lambda cube plus alpha lambda square plus beta lambda plus gamma is equal. Okay, and we equate it to 0, we'll get an equation. So you can find by expanding this set, we can calculate a polynomial like this. And once we calculate the roots for this equation, the roots are given by 28.86, 0.14 and 0. So these are called the singular values. These are called the reciprocals of this. That is 1 by root 28.86, 1 by root 0.14 and 1 by root 0, of course, which is undefined, are called singular values of A. So how do you interpret singular values? Now we are going to define singular values of A. Nothing but singular values of A are nothing but the reciprocals of square roots of eigenvalues of A into A transpose. That's it. So what is the singular value of A? It's nothing but reciprocal of square root of eigenvalue of A into A transpose or A transpose into A. Here we have calculated the eigenvalues of A into A transpose or A into, okay, and the eigenvalues might be some lambda 1, lambda 2, lambda 3. We'll take square roots, root lambda 1, root lambda 2, lambda 3, and we reciprocate them. We'll get 1 by root lambda 1, 1 by root lambda 2, 1 by root lambda 3, which are called theta 1, theta 2, theta 3. Okay, these theta 1, theta 2, theta 3 are given here. These are called the singular values. Okay, and here we can calculate eigenvectors of A into A transpose and A transpose into A, which are given by, because this is a symmetric matrix, we can calculate the eigenvectors by using the homogeneous system of equations. We can calculate eigenvectors which are given by this matrix u1, u2, u3, u1, u2, u3. Of course, we'll see it in the next problem how to calculate these vectors. Now we are going to see a simple problem how to find the singular values of the matrix B. So we have B and or we are taking it as A, and A transpose is again 1, 2, 2, 1, and A into A transpose is nothing but 5, 4, 4, 5. You can easily verify 1, 2, 2, 1 into 1, 2, 2, 1. You can verify 5, 4, 4. Now we are taking the characteristic matrix, the data of characteristic matrix, that is, okay, that is data of 5 minus lambda 4, 4, 5 minus lambda. Data of A into A transpose minus lambda I, that is data of 5 minus lambda 4, 4, 5 minus. When you expand the data with the help of AD minus BC, the formula AD minus BC, you get 5 minus lambda into 5 minus lambda minus 4 into 4. And you equate this to 0, you will get an equation, that is lambda square minus 10 lambda plus 25 minus 16 is equal to 0. That is lambda square minus 10 lambda plus 9 is equal to 0. So what is the equation we got? Lambda square minus 10 lambda plus 9 is equal to 0. And once we get the roots, it is nothing but 3, 1. These are the eigenvalues of A into A transpose. Now we are going to find the singular values. These are the eigenvalues of A into A transpose. Now from these eigenvalues, we will obtain the singular values of the given matrix.
ఎరేజ్ చేయని అవసరం లేదు, కింద ఎరేజ్ ఆప్షన్ డైరెక్ట్ ఉంటుంది. ఇక్కడికి వెళ్తే ఎరేజ్ ఆల్ వస్తే వచ్చేస్తుంది. ఇక్కడికి వెళ్ళండి, ఎరేజ్ ఆల్ ఉంటుంది చూడండి. అండ్ మీరు మాక్సిమం ఇక్కడ చూడండి, ఇక్కడ ఇది ఉంది సిస్టమ్, ఇది ఉంది కోసం మీరు ఇక్కడ చూసే రాయాలి. మొత్తం కిందకే చూస్తున్నారు. మీటింగ్ లో అదే జరిగింది. ఒక్క వీడియో కూడా సరిగ్గా లేదంట, ఆయన నైట్ 1 వరకు చూశారంట, 1 వరకు కూడా ఒక్క వీడియో కూడా సరిగ్గా లేదంట. ఇక్కడ చూడండి,
అక్కడే చూసి
ఇక్కడ చూసి రాయండి. ఓకేనా సార్? మళ్ళీ
రాసేటప్పుడు జనరల్
కిందకి వెళ్ళిపోతుంది ఫేర్. కానీ ఇన్ని రోజులు ఎక్స్పీరియన్స్ ఉంది కదా, మీకు ఎక్స్పీరియన్స్ రోజు వస్తుంది కదా సార్. ఇక్కడ చూసి రాయండి మాక్సిమం. ఓకే, మళ్ళీ డిలీట్ చేయమంటే మళ్ళీ వేస్ట్ అవుతుంది, మళ్ళీ సేవింగ్ చేసి రావాలి మీరు.
చేసాం సార్.
కనిపిస్తుంది అది గడ్డ.
ఓకే
ఓకేనా?
అలాగే.
మళ్ళీ అవన్నీ సార్ చెప్పి మళ్ళీ మీ దగ్గరకు వస్తుంది.
ఓకే సార్. So our question is to find the singular values of the matrix A is equal to 1, 2, 2, 1. We consider this as A is equal to 1, 2, 2, 1. Then the A transpose is, again, it is a symmetric matrix 1, 2, 2, 1. And A into A transpose is 1, 2, 2, 1 into 1, 2, 2, 1. That is equal to 5, 4, 4, 5. Okay. And the characteristic polynomial given by the formula A into A transpose minus lambda I, which is det of the matrix 5 minus lambda 4, 4, 5 minus lambda. By expanding the det, we get 5 minus lambda into 5 minus lambda minus 4 into 4. That is lambda square minus 10 lambda plus 25 minus 60. Lambda square minus 10 lambda plus 9. So we got the characteristic polynomial as lambda square minus 10 lambda plus 9 is equal to 0. So characteristic equation is nothing but lambda square minus 10 lambda plus 9 is equal to 0. By solving this equation, that means lambda, by solving this equation, we'll get the roots 3, 1. So these are the eigenvalues. These are the eigenvalues of A into A transpose. Okay. So once we get the eigenvalues, lambda is equal to 3, 1. Eigenvalues lambda is equal to 3, 1 for the matrix A into A transpose. Now let us calculate the square roots, that is root lambda, that is root 3, root 1. Root 3 is 1.732 and root 1 is 1. Now let us take the reciprocals, 1 by root lambda, that is 1 by 1.732, 1 by 1. These are called the singular values theta 1, 1 by 1.732, theta 2, 1 by 1. These are called the singular values. So in this way, we can calculate singular values for a given 2 by 2 matrix, which are represented as theta 1, theta 2, which are nothing but reciprocals of the positive square roots of the eigenvalues of A into A transpose. So the reciprocals of positive square roots of eigenvalues of A into A transpose are called the singular values of the matrix A. Okay. Now we are going to see the singular value decomposition of a given matrix A, which is of order 3 by 3. And for this, we need to calculate A into A transpose. A into A transpose, that is 0, 1, 1, root 2, 2, 0, 0, 1, 1, 0, root 2, 0, 1, 2, 1, 1, 0, 1. This is the product of A into A transpose, which is equals to 2, 2, 2, 2, 6, 2 and 2, 2. So this is represented here. This is our matrix A into A transpose. Excuse me. Now, by writing the characteristic polynomial formula det of A into A transpose minus lambda I, we have 2 minus lambda 2, 2, 2, 6 minus lambda 2, 2, 2, 2 minus lambda. By expanding this det, we'll get this equation. And we can factorize. And the factors are lambda, lambda minus 8, lambda minus 2. By equating this to 0, this det to 0, we'll get an equation, characteristic equation equal to 0, and hence we get the roots 0, 8 and 2. These are the eigenvalues of A into A transpose. Okay. Now, let us proceed to the next step. Of course, I'll give the brief explanation or the next step of the procedure, and then I'll, with the help of calculation, I'll explain how we arrived at that steps. Here, A transpose A, okay, is this matrix, and again will result into the same eigenvalues 8, 2, 0 for this matrix also, and the eigenvectors which are normalized eigenvectors for the matrix A transpose A. For the matrix A transpose A, the eigenvectors will be, after normalizing, we'll get Q1, Q2, Q3. Let us see how we'll obtain those matrices. Let's go back to the previous slide. Yes, when we have A into A transpose, A into A transpose, and the eigenvalues of A into A transpose are lambda is equal to 8, 2, 0. Now, I'll explain how to get eigenvector with the help of eigenvalue 0. Okay, so for that, I am considering the matrix A into A transpose minus lambda I, which is nothing but 2 minus lambda 2, 2, 2, 6 minus lambda 2, 2, 2, 2 minus lambda. Okay, here I am substituting lambda is equal to 0. I am substituting lambda is equal to 0. So A into A transpose minus 0 I, that is equal to 2 minus 0, 2, 2, 2, 6 minus 0, 2, 2, 2, 2 minus 0. So hence we get the matrix 2, 2, 2, 2, 6, 2, 2, 2, 2. After substituting lambda is equal to 0, we got this matrix. Now, from these three rows, we can write three equations like this. 2x1 plus 2x2 plus 2x3 is equal to 0. 2x1 plus 6x2 plus 2x3 is equal to 0. 2x1 plus 2x2 plus 2x3 is equal to 0. So these are the three equations which we have obtained from this. Okay. Now from these three equations, we default choose x3 as 1. Okay, by default we'll choose x3 as 1. Okay, then these three equations becomes like this. 2x1 plus 2x2 plus 2, that means is equal to minus 2. 2x1 plus 6x2 is equal to minus 2. 2x1 plus 2x2 is equal to minus 2. Here, because first and third equations are same, we can ignore one equation. So we are left with these two equations, equation 1 and equation 2. Now, let us solve these two equations. We can cancel two tables, one time, and one time. Two tables, one time, 3 times, and 1. So the equations becomes x1 plus x2 is equal to minus 1. x1 plus 3x2 is equal to minus 1. By subtracting these equations, we get x1 minus x1 cancelled, x2 minus 3x2, that is minus 2x2, and minus 1 with the minus 1. By adding, we are adding, so that becomes minus 1, that becomes minus 2, and hence x2 is, we get 1. Now, after getting x2 is 1, so x2 is 0, we are getting x2 is 0. Okay, x2 is 0. And by substituting x2 in this equation, we get x1 is equal to minus 1. And automatically, already we have chosen x3 is 1. So what is the vector we got? x1, x2, x3. x1, x2, x3. x1 is minus 1, x2 is 0, x3 is 1. Okay, let us say this as x. Now let us take norm x. Norm x means root of minus 1 whole square plus 0 square plus 1 square. That is root 2. Okay, so we got norm x as root 2. Let us construct x bar as minus 1 by its norm, that is root 2, 0 by root 2, and 1 by root. This is the first vector we obtained with respect to the eigenvalue lambda is equal to 0. In the same way, we can obtain the eigenvector corresponding to lambda is equal to 2 and the eigenvector corresponding to lambda is equal to 8. Okay, let us see one more example. I'll explain how to get eigenvector corresponding to lambda is equal to 2. And you can understand the same way how to construct eigenvector with respect to lambda is equal to 8. Yes. Now we are going to see how to get eigenvector corresponding to lambda is equal to 2. So for that we need to find A transpose minus 2i. That means 2 minus 2, 2, 2, 2, 6 minus 2, 2, 2, 2, 2 minus 2. So the resultant matrix is 0, 2, 2, 2, 4, 2, 2, 2, 0. With this, we can write equations as 2x2 plus 2x3 is equal to 0, 2x1 plus 4x2 plus 2x3 is equal to 0, 2x1 plus 2x2 is equal to 0. Here, to solve these three equations, we can ignore any one of the equations. Default, we are ignoring the third equation. We are considering these two equations only. So, from these two equations, we will substitute x3 as 1 in default. As just we have done in the previous case, we are substituting x3 is equal to 1. Then, first equation becomes 2x2 plus 2 into 1 is equal to 0. So, x2 is equal to minus 1. And by substituting x2 is equal to minus 1 and x3 is equal to 1 in second equation, we get 2x1 plus 4 into minus 1 plus 2 into 1 is equal to 0. 2x1 is equal to 2 and x1 is equal to 1. So the resultant vector is x is equal to x1, that is 1, x2 minus 1, x3 1. And the norm of x which I am going to calculate here, norm of x is root of 1 square plus minus 1 square plus 1 square, that is root 3. So we can write the normalized vector, orthogonal vector x bar as 1 by root 3 minus 1 by root 3, 1 by root 3. In the same way, you can calculate the other third vector with respect to the lambda is equal to 8 also. So by using this procedure, we can calculate the eigenvalues and eigenvectors of A into A transpose as well as A transpose into A, which are normalized eigenvectors we are calculating. So here we get the eigenvalues 820 for A transpose A and the eigenvectors Q1, Q2, Q3. Now, with the help of these eigenvalues, we can write Q as the vectors just we obtained there, that is Q1, Q2, Q3. So this is our Q. Okay. And we can calculate Pi by using the formula 1 by sigma I A transpose Qi. This is the formula. That means we have obtained Q1, Q2, Q3. In the previous slides, we have obtained Q1, Q2, Q3. Now we'll calculate sigma 1, sigma 2, sigma 3. Then we come to P1, P2. Let us see how to calculate sigma 1, sigma 2, sigma 3 first. See, we have obtained the eigenvalues. Lambda 1 is 8, lambda 2 is 2, lambda 3 is 0. Then root of lambda 1 is root 8, root of lambda 2 is root 2, and root of lambda 3 is 0. The reciprocal 1 by root lambda 1 is 1 by root 8, 1 by root lambda 2 is 1 by root 2, and 1 by 0, that is infinity. So 1 by root lambda 3 is infinity, undefined. So these are called sigma 1. Sigma 1 is 1 by root 8, that is 1 by 2 root 2. Sigma 2 is 1 by root 2. And sigma 3 is undefined, infinity. So these are sigma 1, sigma 2, sigma 3. This way we calculate the singular values, which in the previous problem we discussed them as theta 1, theta 2, theta 3. But here we can also use the symbol sigma 1, sigma 2, sigma 3. Okay, now our formula is, to calculate P1, our formula is 1 by sigma 1 A transpose Q1. Here misprint, it is Q1. Okay, so 1 by sigma 1 means 1 by 2 root 2. A transpose we can write from the given question, and Q1 we have obtained in the previous calculations. So when we multiply this, we'll get P1 like this. Okay, then we can get P1. Similarly, we can write P2 as 1 by sigma 2 A transpose Q2, and P3 as 1 by sigma 3 A transpose Q3. And in that way, we can calculate the matrix capital P. And we will write the matrix summation as 1 by sigma 1, 1 by sigma 2, 1 by sigma 3, and 0, 0, 0, 0, 0, 0. That is 1 by 8, 1 by 2, okay, and 1 by 0. That you can also take 0 or infinity. 0 you can take, and 0, 0, 0, 0, 0, 0. Sorry, 1 by root 8, 1 by root 2, and 0. Instead of infinity also we can take 0. Because it is undefined, we put default as 0. Okay, this is our sigma, and we have calculated P, and we have calculated Q, and we can write Q transpose. And if you check P into sigma into Q transpose, we'll approximately get the original matrix A, and we have successfully decomposed A into product of three matrices P, sigma, Q transpose. Let us look into the question first. So this is our question, and we have decomposed it into three matrices P, sigma, Q transpose, where Q1, Q2, Q3 comprise of Q. Q1 comprise of Q, that is Q1, Q2, Q3. Okay, and from this Q, by using the formula P1 is equal to 1 by sigma 1 A transpose Q1. Similarly, P2, P3, we can calculate the matrix P is equal to P1, P2, P3. And you can calculate the summation matrix sigma as 1 by sigma 1, 1 by sigma 2, 1 by sigma 3. Okay, and remaining all zeros. And in this way, we are obtaining the singular value decomposition, that is A is equal to P sigma Q transpose. So this is the working procedure, mathematical working procedure of decomposing a matrix A into product of three matrices P summation Q transpose, which is called singular value decomposition. So with this, we conclude this lecture, and I hope we understood the process of calculating the singular value decomposition for a 3 by 3 matrices. Okay, and in the next class, we'll see how to find pseudo inverse by using singular value decomposition for a given matrix. And thanks for your patience listening, and we'll meet in the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.